Morning, good afternoon, and good evening, everybody. I am Supriyo Chakraborty from Indian Institute of Tropical Meteorology, Pune in India. First, I would like to thank Dr. Soderman and his team for arranging this workshop and giving me an opportunity to present our work. So far, we have seen most of the observational program from the high latitude areas of the Arctic and temperate regions. In this talk, I would like to present the results of the precipitation isotopes analysis that we have been carrying out in an island in the equatorial Indian Ocean region for the last several years. The hydrological cycle in the southeastern region is predominantly dominated by the monsoon processes. Around the first week of June, a strong cross-equatorial circulation sets in, which brings tremendous amount of moisture from the Indian Ocean region that causes abundant rainfall all over the country. This is termed as Indian summer monsoon or the southwest monsoon. After about 4 months, the circulation gets reversed. The air starts coming from the east and northeast region, which is termed as northeast monsoon, which is shown here by these red arrows. Blue arrows indicates the southwest monsoon. The study of monsoon has immense importance as the economic activities and the agricultural practices greatly depend on the monsoon rainfall. So the study of precipitation isotopes in the Indian context is intricately related to the monsoon processes. One of the attributes of the monsoon system is the monsoon onset and the withdrawal timing, as this information is necessary for sowing of crops. During the monsoon onset phase, sharp changes in meteorological variables are observed. Within a few days, rainfall increases and the low-level winds become very strong at the South Peninsular coastal region of India. Hence, monsoon onset can be determined with reasonably high precision. But during the withdrawal phase, the atmospheric variables suffer from slow changes. As a result, monsoon withdrawal date often experiences a large range. We have investigated how the precipitation isotopes in this region respond to wind circulation and thereby how it could be used to better understand the monsoon process. Hence, the title of my talk is Estimation of Monsoon Withdrawal Date in Southern India using the isotopic techniques. As said, India experiences two distinct circulation regimes, the summer and winter monsoon circulation. During the summer, precipitation is reasonably high and it spreads almost all over the country. During the winter, the rainfall is restricted to a few states in southern Indian region. Expectedly, high rainfall amount causes more depletion in precipitation isotopic values. For example, this figure shows the delta of rainfall observed in New Delhi, a site in northern Indian region. As shown in July, the rainfall is high and delta gradually decreases, and it reaches a minimum around September. But in winter, when precipitation is low, the delta shows an increasing trend. But this pattern shows opposite behavior in a narrow latitudinal belt as shown by the shaded regions in this figure. Some investigators reported that delta of rainfall in South India and also in Sri Lanka have relatively high values in summer and low values in winter. For example, Warrior et al. Have shown that the isotopic values of rainfall at a place in South India called Kozhikode is high in summer and low values in the winter. We have also observed similar behavior in the isotopic values of rainfall at Port Blair, an island in Bay of Bengal. The summer to winter isotopic gradient is approximately 3 per mil. Similarly, we have also observed similar behavior at another island, the Minicoy Island in the Arabian Sea region. The reason for having such an opposite isotopic seasonality is due to the reversal of the circulation regime. During this summer monsoon season, the flow is predominantly southwesterly. The circulation brings moisture from the Indian Ocean and the Arabian Sea, while during winter, the moisture is transported from the South China Sea, Western Pacific, etc. We have been studying the precipitation isotope variability in the Andaman Island region for the last few years. In an earlier work, we investigated how do the isotopes of vapor and rainfall interact with each other. In 2015, we estimated that isotopic values of rainfall on an average got enriched by about 0.41 per mil due to its interaction with the ambient vapor. In this work, we try to address the following scientific questions: to explore the relation between monsoon circulation and precipitation isotopes, to investigate how the precipitation isotopes respond to thermodynamic characteristics of the atmosphere, to identify the summer to winter monsoon transitional phase using the isotopic technique. The method is described in this slide. We collected precipitation samples from 3 locations, 2 island locations. One is Minicoy Island in Arabian Sea and one is Andaman Island. The site is Port Blair in the Bay of Bengal, and another inland station, Trivandrum, in southern India. To quantify the monsoon intensity and its variability, we used 2 monsoon indices. Monsoon index is defined by several means. Most used is the area average rainfall. So that is the defined in Parthasarathi et al. 1992. And the other one is the circulation index. Webster and Young defined in this index, which is the average values of zonal wind at 850 and 200 hectopascal levels, and calculated at this latitude and longitude band shown here. The difference between these values essentially defines the wind shear. It is used as monsoon variability both in interseasonal and interannual timescales. On the other hand, Xavier et al. Formulated another index, which relies on the difference between the tropospheric temperature. In this case, 2 vertical boxes are considered as shown here by red box and blue box over the Indian region. The southern box lies below the equator and the northern box above the equator. The temperature difference between the northern box and the southern box is termed as the tropospheric temperature gradient, and it is used as a monsoon index. The temperature difference is usually negative, except during the monsoon season. According to the authors, when the temperature difference is positive, monsoon sets in over the Indian region. It remains positive throughout the monsoon season and again turns negative when southwest monsoon is withdrawn. The basic feature of this index is the shift in the tropospheric heat source. Huge amount of latent heat is released during the monsoon season. So northern box over the Indian region acts as a heat source. Once the monsoon is withdrawn, the heat source shifts to the southern hemisphere. We would examine whether the precipitation isotopes are sensitive to these heat sources. Here, this one shows the tropospheric temperature difference. In a strong monsoon season, this difference is high. In a weak monsoon season, as in during the El Nino years, this difference is low, shown by this red line. This slide shows the variability of delta 18O and its covariations with the Webster-Young index. We see that these 2 parameters show strong covariation. That is, both of them are high in summer and relatively low in winter. This kind of covariation provides a means to identify the summer and winter monsoon season using the isotopes, which I'll discuss a little later. This slide shows the variability of other atmospheric variables during the monsoon withdrawal phase. These are the rainfall, precipitable water, and the isotopic values over the Andaman Island region. We see significant differences during the withdrawal phase as shown by the setting. Now, how we calculate the withdrawal date, this is explained here. First, we make a scatter plot between the WY index as x-axis and delta I2 as y-axis. As shown in this slide, they form two distinct clusters. During the summer, both WY index and delta I2 are high, so they tend to cluster in this region that is shown by this reddish box. And similarly, during the winter, they show relatively low values, so they are shown here in the gray box. Now we level these points and we find what is the last date in the summer box and what is the first date in the winter box. If the sample resolution is high, then this band, so-called the withdrawal date band, will be low, that is precision will be high. But if sample resolution is less, as in this case, we can have a wide band. For example, in this case, the band is 3rd September to 14 November. But in other cases, for example, this is Trivandrum in inland region, we get a dead band of 26 September to 13 October, which is quite improved because the number of samples are collected more in this site. In case of Port Blair, we had more number of sites and hence the date band is much better, which is 8 to 15th October. Similarly, and this figure shows the onset and withdrawal date calculated using the tropospheric temperature difference. The withdrawal date estimated in this method is 11 October. What we see here that isotopic method has a band about 8 to 15 October, and delta TT method or the tropospheric temperature method shows 11 October, so they match quite well. Similarly, we have calculated for other years. So I will skip this and I will show the table which shows the date bands for all the years and for the different sites. What we see here is that this is the isotopic methods date band, and these are the methods in the last but one. This shows the method estimated by tropospheric temperature difference, and this is made by IMD, that is Indian Meteorological Department. It is to be noted that isotope-based withdrawal dates match reasonably well with that estimated by the tropospheric temperature difference method, but it considerably differs from that obtained by the method followed by the IMD. These results show that precipitation isotopes respond to the tropospheric temperature difference. In the year 2017, estimates carried out by all the methods match very well. This means that the criteria of monsoon withdrawal estimation fulfilled by each method agreed quite well. On other words, we can say that the dynamic and thermodynamic conditions during the summer season and during the winter seasons are well resolved. So this resolution is manifested in the precipitation isotopes. So the precipitation isotopes, though measured on a point scale, can be used to study the large scale processes. So here is the summary of the top. The isotope-based withdrawal test, it matched quite well with the tropospheric temperature difference method. This means it responds to tropospheric heat sources. Precipitation isotopes in the South Peninsular India respond to large-scale monsoon indices, which the Western Circulation Index and the thermodynamic index proposed by Xavier et al. So these characteristics show their potentials to study the monsoon processes in a different perspective. Thank you.